In our previous class, we have covered that how to compute the equivalence between the two classes of PDA, that is, whether a PDA is being constructed by considering the fact that okay, this string will be accepted by the final state, or the stack will get emptied. Both are same. So in our previous class we have seen that if we can empty the stack, if that string is being accepted by the empty stack, then it will obviously reach the final state. But in this lecture we will just see the reverse condition, that if we can establish that okay, this string, the PDA can with the help of this string, the PDA is able to reach the final state, right? Then it will also empty its stack simultaneously. So from final state we will move to the concept of empty stack in this lecture. Fine. So just look at the diagram. So what we are doing here, we have incorporated one state, namely P naught, and another state, namely P. Let us see what are the usage of these two. What this slide is saying, that from each accepting state of PF is all the states which are final state, right? There can be more than one final state, so we are considering the set of final states as P of F. So from each accepting state or final state, we are adding a transition of epsilon to a new state P. That means nothing. Say, just keep in mind that here we will focus on, means from PF we have to move to PN, right? So what we have to do, whenever we will see that okay, a PDA has reached its final state, we have to empty the stack, right? That is our final goal. So whenever we will see that, when we will see that okay, this has been accepted by the final state, so ultimate what is the scenario, that with the help of this string the PDA is able to reach its final state. Now whenever it will reach its final state, with epsilon move we will just empty the stack, right? So whatever the state comes under the set of P of F, we will just apply one epsilon transition and we will move to a new state called P, just to empty the stack, nothing else. It is not going to consume any input, not doing nothing, just to establish the concept. The thing will happen simultaneously actually. Whenever it will reach the final state, automatically the stack will get emptied, but we have to establish it diagrammatically or theoretically. That's why we are incorporating one more step to make it clear that okay, whenever it has reached P of F, we will, with the help of epsilon transition, so there is no concept of consuming input, there is no concept of changing the top of the stack, nothing. We are just coming to the conclusion, okay, my stack has got emptied. Fine. Next, when in state P, whenever it will be in P, PN means what? The PDA which acts with the help of the concept of emptying the stack. That is we denote it by PN. If you follow the previous lecture, we have discussed there that what is PN, what is PF, and all other things. So when in state P of n will pop its stack and does not consume any input. I have already told you the same thing. Fine. Now, thus whenever PF enters an accepting state after consuming input, PN will empty its stack after consuming W. The thing is same, right? So whenever we have seen the concept of getting accepted by the final state, what we did, whenever the total input gets consumed, it will do what? It will reach its final state. Here we will do what? Whenever it will consume all its input, there nothing remains with W, the stack will get empty, right? This much. Okay, to avoid simulating a situation where P of F accidentally empties its stack without accepting, Pn must also use a marker x0 on the bottom of its stack. It is saying nothing. If PF empties its stack and without accepting the string, right? This situation may occur. So for this reason we are just if you remember that in case of P of f, we have used the symbol or the marker x naught as the beginning part, right, to initiate the stack. But here we will keep that x naught at the bottom of the stack to just to use it as marker. Okay, we have reached the bottom of the stack, right. The situation may be like this, that the pf has empties its stack without accepting, so the situation is wrong, right. This should not happen. So to make that thing to make this pn aware of it, we will just use one marker x naught, which will just mark that we have reached the bottom of the stack. Okay, the marker is Pn's start symbol. Pn must start in a new state P0, whose sole function is to push the start symbol of Pf on the stack and go to the start state of Pf. Just look at the diagram, what it is doing. Firstly, the stack is empty, right? But if you remember the previous way of accepting the string that is getting accepted by final state, what it will do, it will always push z0 to it will be used as the marker that okay, we have reached. Whenever z0 is at the top of the stack, we will think that okay, we have to pop z0 and my stack will become empty in case of acceptance by final state. So here, since we are using the concept of final state, we are moving to emptying stack concept. So we have to mimic whatever pf is doing, right. Pn has to just copy it down or simulate it down. That's why we also have to push z0 onto it. The sole responsibility of p0, just if you see the diagram, it is very clearly mentioned there. It is just pushing z0 and doing nothing else. Okay, fine. So now we will focus on the theorem. So what theorem is saying, let L be L of pf. L of pf means the language which p of f accepts, means the language which gets accepted by the final state in case of PDA. Fine. So it will be described by this notation. We know the meaning of all the symbols mentioned in the tuple here, what q means, what sigma means, what tau means, and so on. And from this concept, assuming this pf, we will come to the conclusion, if this exists, then there is also a language L which this same L will get accepted by the machine or the PDA, which just come to the conclusion by emptying its stack. Okay, so we will just prove that L of pf is same as that of n of pn. In a previous lecture, we have just proved the reverse one. Here the situation is just reverse. Okay, so what we have to prove here, we are assuming one concept. We are just assuming the machine Pn or PDA Pn. Like, just see, it will have everything similar. It will have all the states as of P of f, that is that will come under the set Q. And in addition to that, there are two more states added. One is P0, whose sole responsibility is just to push the Z0 onto the stack, and P. What P is doing, we have already discussed. For any set in PF, it will just from P of any of the PF, we will just make one epsilon transition, and the job is to empty the stack, right. Okay, then sigma is same, all the set of all input symbols tau is there, and we have added if you just follow the previous one, there also we have added x naught, right. Job of x naught, it does not belong to in tau, means it is not anything specified function there, it is just means it is not a defined stack symbol, right. We have nothing to do with it. It will just act as a marker. That's why you have written it separately, because you cannot say that this is a part of tau itself. It's not a part of tau at all. It is just a symbol, stack symbol definitely, but it will be act as, or it will be used as a marker, nothing else. Fine. Then delta n, all the transition functions. P0 is your start symbol, and x0 is using as a bottom of the stack. Fine. Okay. Now let us see what delta n will be doing here, right. Say for for the first one, for the state p naught, and for any symbol for empty symbol, and this x naught is the marker, what we will do, just see the first transition from start symbol p naught to q naught. What it is doing, it is just pushing z naught. So x naught was already there because it is acting as a marker, and to mimic pf we have to insert z naught as well, so it is just pushing it. Fine. Okay, this much is clear. Next, what it will do, whenever it, after q naught, means whenever it has just entered the start state of pf, it will just copy what pf is doing. It is just written here, just see, for all states small q in capital Q, means for any of the states available, for any of the input symbol a, any, it can be any input symbol belonging to sigma, including empty input means of your epsilon, and y in tau for any stack symbol. What it is doing, delta n of q of a y contains every pair that was in that of delta f. So this part will get totally copied, nothing to worry. Fine. Next, for all accepting states q in f and stack symbol y in tau, or y equals to x naught, means it has reached the bottom part, x your marker. So delta of n, what it will do, it will contain a pair of p of epsilon. Why? Because whenever it has reached the accepting states, that means it is under the surveillance of p of f. So whenever we are in any of the accepting states which belongs to p of f, what we are going to do, for any epsilon transition, we will just add epsilon transition, we will move to the state p, that is written here, and it will definitely not consume any input because there is no input symbol remains to get consumed, right? Everything gets already got being consumed by the machine, otherwise how it would be able to reach the final state. Okay. Now next is, for all stack symbols y in tau or y equals to x naught, just see the same thing, we are assuming any other conditions. Once in state p, which occurs when p of f has accepted, p of n pops every symbol on its stack until the stack is empty, no further input is consumed. The same thing is being done whenever it has reached p, means once it has reached p, so its job is to empty its stack. So means why it is going to empty its stack again whenever it has already been emptied, because if you remember that in this case we are just adding one symbol x naught to mark this p of n, that okay, you have reached the end of the stack. So here it will empty everything, because whenever it has reached pf, that means it has consumed all the inputs. Again, just it will move to another state p, just it will see, okay, only x naught remains, that is I have reached the end of the stack, so we will pop everything. So stack got emptied, and that means the string has been accepted. Now how to prove that these two are similar? Now we must prove that W is in NPN if and only if W is in LPF, right? The idea are similar to the proof of the previous theorem. If part is a direct simulation, and only if part requires that we examine the limited number of things that the constructed PN can do. We will see. We will again in the similar fashion. We will just firstly prove the if part. It will be very easy, and for only if part we will just consider a few conditions. Fine. So if you follow the theorem, so if part is saying that suppose. Just see what it is doing. We are at q0, right? So we are at q0 means here we are going to copy everything what pf is doing. So we are at q0, we have w with us and we have z naught with us. That means we are just in the initiation part. Total w remains, but because we have not yet scanned any of the symbol, and z0 means the initiation of the stack. So for whatever the transition pf is doing, we will do the same thing, and at the end of the day we will just reach to the state q, and it w becomes epsilon, means that nothing remains, and everything is done. Alpha means my stack symbols, it has been changed, the top stack symbol has been changed, so it is just copying pf. Okay, for some accepting state q and stack string alpha. So if you just follow this path, just see what it is, what pn is doing. This one, just from p0 it is having w with it. So beginning, what is the stack condition now? x0, right? We have not entered q0 yet. From the beginning, from the start symbol, I am saying it is p0, and the total string remains, that is w, and x0 is there in the stack. So what it will do? It will move to q0, w, just see w remains, because we are not consuming any input part. What we are doing, we are just pushing z0. Why? Because now we will copy the total functioning of pf. That's why we are putting z0. Now from here, it will act similarly like pf, and if you see that after these many transitions, what it is, where it is moving, it is having alpha with it. I'm talking of the stack symbol. It is having alpha with it, but again it has x0 with it, because it is acting as a marker. So whenever this situation comes, it will do what? It will directly move to p, and it will empty its stack, right? Okay, now let us come to the only if part. The only way pn can empty its stack is by entering state p, since x0 is sitting at the bottom of the stack, and x0 is not a symbol on which pf has any moves, right? So since we are to make the pn aware that okay, you have reached the bottom of the stack, we are using a marker x0. But if we cannot copy pf in this situation, because pf has no moves with x0, it has nothing to do with it. So whenever it will see x0, it has to move to p and empty it up there. It has to work it of its own. Okay, the only way pn can enter state p if the simulated pf enters an accepting state, obviously. So if it has entered the accepting state, that is any state under pf, then only it can move to p. The first move of pn is surely the move given in rule 1, right? So just see here, for any epsilon, it will be at p, and the job is to empty the stack, nothing else. So thus we can come to the conclusion that if you see this symbolic part, so if we write the whole thing as in this fashion, it is nothing to worry of, because we have explained each and every step, how from the start symbol it is moving to q0, from q0 how it is just copying or simulating p of f, and then for how it can move to p, under which conditions, right? So this is very clear. So what we have done here, so here between the two IDs, that is q0 w z0 x0 and q epsilon alpha x0, all the moves are moves of pf. So I have already explained you the same thing if you consult the previous slide again. So you can see that we have added two features at the beginning, that is from p0 how we can move to q0, and from p of f how we can move to p, right? These two stages are different, and whatever the in between part is there, it is totally same as that of p of f. Fine. So this much in this lecture, and next we will learn, it's a very important topic, that is how context free grammars and PDAs are equivalent. We will see it in our next lecture. Okay, thank you.